What is momentum? Momentum is a quantity found by multiplying the mass and velocity of an object together. Because velocity is a vector quantity, so is momentum. A vector quantity has both a magnitude and a direction. Let's begin with some basic momentum calculations. Ball A, has a mass of 2 grams and a velocity of 2 meters per second. Its momentum is found by multiplying the mass and velocity together to get a momentum of 4 Newton seconds. The second ball B, has a mass of 0.5 kilograms and a velocity of 6 meters per second. Its momentum when calculated is 3 Newton seconds. Ball C has a mass of 1 kilogram and a velocity of 3 meters per second. Its momentum is found to be 3 Newton seconds. Conservation of momentum relies on defining a system. We're going to have option 1 and option 2, with system A and system B. In system A, momentum is not conserved because of external forces being applied. However, system B is defined with only internal forces, meaning momentum will be conserved after the collision. Therefore, the initial momentum will always equal the final momentum, a system defined only with internal forces. The first type of interaction we're going to discuss is perfectly elastic collisions. Perfectly elastic collisions have no loss in kinetic energy, the momentum is conserved, and the final velocities will typically be in opposite directions. Perfectly elastic collision calculations begin by drawing out the before and after scenarios, labeling all the given information. For this problem, cart 1 has an initial velocity of 2 meters per second, and cart 2 has an initial velocity of 0 meters per second, masses of 3 kilograms and 6 kilograms respectively. The final velocity of cart 1 is negative 0.5 meters per second, with cart 2's final velocity being unknown. Using the conservation of momentum, the initial momentum of cart 1 plus the initial momentum of cart 2 equals the momentum of cart 1 plus the final momentum of cart 2, with the final velocity of cart 2 being unknown. The final velocity of cart 2 can be solved algebraically. Problem 2 is going to be set up in the same way as problem 1. The initial velocity of cart 1 is 3 meters per second with a mass of 2 kilograms, and the initial velocity of cart 2 is negative 3 meters per second with a mass of 4 kilograms. The final velocity of cart 1 is unknown, and the final velocity of cart 2 is 2 meters per second. Using conservation of momentum, the initial momentum is set equal to the final momentum, and using algebra to solve, the final velocity of cart 1 is equal to negative 7 meters per second. The second type of interaction are inelastic collisions. They have a loss of kinetic energy. Momentum is conserved, but the final velocity is in the same direction. Inelastic collisions are set up in the same way as elastic collisions, labeling all known information. However, for the final velocity of an inelastic collision, because both carts move as the same entity, they will have the same final velocity. Solve using the conservation of momentum in algebra. Slow down the video and watch problem 4 to see that a cart with the initial velocity of 0 does not change the behavior of an inelastic collision. The third type of interaction are explosion. In an explosion, both objects have an initial velocity of 0 meters per second. Movement after the interaction is in opposite directions. Explosion problems are set up in the same way, with the initial velocity of both objects being 0. Both objects in this situation have different masses. However, the final velocity will be in opposite directions. Set up using conservation of momentum, solve using algebra to find the final velocity of object 2. These calculations involve a few assumptions. First, elastic collisions are assumed to be perfectly elastic. Second, we assume the track is frictionless and thus don't take friction into account when solving for momentum. Impulse is an external force applied over time. When it is applied, initial momentum no longer equals final momentum. It is found by multiplying the force times the change in time. Because force is a vector quantity, impulse is also a vector quantity, defined by the letter J. The initial momentum plus the impulse equals the final momentum, and this is now the updated conservation of momentum formula. For problem number 6, we're going to set it up in the same way as the other problems. However, for this problem, we're going to have a single cart acted by an external force to change the velocity. The object has a mass of 5 kilograms and an initial velocity of 4 meters per second. The velocity will change to 6 meters per second by a force of 5 newtons over an unknown amount of time. Using conservation of momentum, the initial momentum plus the impulse equals the final momentum. Solve algebraically to find the change in time to be 2 seconds. Momentum in multiple direction calculations. We're going to involve taking momentum into account from x and y. For this problem, we're going to look at a pool table with 2 balls resting on it. Ball A, the orange ball, has some momentum purely in the horizontal direction to begin with, and ball B is initially at rest. After collision, in which the two balls collide, ball A has a non-zero velocity as well, but it's at an angle, and ball B also has a non-zero velocity at an angle as well. Ball A has an initial velocity of 5 meters per second, and ball B has an initial velocity of 0. Both balls have a mass of 0.25 kilograms. Ball A's velocity is going to change to 3 meters per second at a 30-degree angle. Ball B has an unknown final velocity. So looking at momentum in the x direction, the horizontal momentum of ball A, the mass times its horizontal velocity, plus the mass of ball B times its horizontal velocity, 0, is equal to the final momentum, the mass of ball A times 3 cosine of 30, plus mass of ball B times x, unknown. So I'll algebraically define that it's 2.4 meters per second. Do the same thing for the y direction. Because both balls have a momentum in the y direction of 0, the left side of the equation is going to equal 0. On the right side, we're going to do the mass times 3 sine of 30, the y component of the velocity, plus the mass times the unknown y component of ball B. So often find the y component of the final velocity for ball B to be negative 1.5 meters per second. Using trigonometric properties, we're going to find that the final velocity for ball B is 2.83 meters per second. And again, using trigonometric properties, we're going to find that the direction of this motion is 32 degrees. So ball B is moving at 2.83 meters per second at 32 degrees down from the horizontal.